Hello guys, welcome to the mind map series, and in this particular mind map we are going to discuss optics or the study of light. As you must be already knowing that light has two properties. It behaves as a particle nature, and wave nature, both. It has a dual nature. So in this part 1 of the mind map we are going to discuss particle nature, and then in the second part, which is this one, we will discuss the wave nature. All right, let's start. um, See, let me make it, this is better. Now, uh, first of all, let's talk about some very basic properties. I'll just give you a gist of it. First of all, light has some properties. Law of reflection, that if it's any surface, let's say this surface, if light is coming in this direction, it will be reflected in such a manner that if you draw perpendicular to this point to the surface, then the angle of incidence I will be equal to angle of reflection. This is the law of reflection. And there is another law, we'll talk about it later. But based on this, we draw something called a ray diagram. Basically, we track the rays coming from a particle, and then whatever it is doing, passing through a prism, passing through, or reflecting from a mirror, things like that. First of all, if there is any optical instrument, let's call this mirror, a plane mirror. We will have a horizontal line which is called principal axis, and let's say this is the object. I'll draw the light rays. Then uh, let's draw a ray diagram. What we'll do is, probably we can pass it from this point, and then it will get reflected in such a manner that this angle should be equal to this angle as per our uh, property of light. This is the plane mirror, and we can use another. Let's do this. Then it will get reflected in such a manner. All right. Now, when you try to join them, see, they are divergent, right? They are divergent. They are not going to join each other anywhere in future. So if a person is looking from here, if a person is looking from here, then he will see that light rays are coming in this direction to the eyes, and they seem to be originating at this point, right? So the object appears like this. Is this a real image? No. Why? Because light rays are not exactly touching each other or crossing each other and forming an image. It is rather the imagination of the mind of this viewer that the light must be coming from this particular point. That is why he will see a virtual image. I'm all talking about a ray diagram here. So this is the principal axis. Now, yeah. So while applying, we have certain formula for this. Whatever the direction of light is there, let's say the object is here, and this is the optical instrument. Any optical instrument could be there, a lens, a mirror, a spherical mirror. Then in this direction, from the optical instrument, in this direction where the light must be going from the object, the direction of propagation of light is called uh, positive. We take it as sign convention. This then becomes negative. and the upward and lower direction are positive and negative. All right, so this is the sign convention we will follow, although it doesn't matter, but it is easier when everyone follows the same sign convention so that there is no confusion. So pole is taken as origin. This is the point, pole, where principal axis uh, dissects the this whatever optical instrument you have. This is called pole. Principal axis we already talked about. All distances are measured from the origin. It means if you have this object at here, then you'll find this distance x, and you'll say that the position of this object is minus x, because we always define it from the pole. Whether it is positive or negative, it will depend on the relative position of the this thing object. And all distances are measured in this, we have already discussed the sign convention. Now let's talk about something called, or let's talk about spherical mirrors first of all. This is a plane mirror, right? Plane mirror. We also have something like this. Let's say this is a spherical shell. What I do is cut a section, of spherical mirror, or sorry, spherical shell, and we get something like this. Now we have two open faces. In the mirror, what happens is we silver one of the faces so that light can reflect from the other one. In the same manner, we have two faces, both could be silvered. Let's say we silver this one. Then it becomes a convex mirror. Convex mirror. And if we silver this side, it becomes concave. For those of you who don't, who fail to remember what is convex and what is concave, they get confused. You might use it as a like thing to remember. It is a concave, right? So cave is often like a hollow place, right? So a light can enter a hollow place, then it is called concave. So convex and concave mirror. Light will come, let's say we draw the principal axis on this one. Then it must pass through the center of the instrument, right? And this is the pole now. And objects could be placed here. And let's say they reflect back, because they always reflect back from the following the angle of this law of reflection, right? Incident angle is equal to reflected angle, and this could be like this. Incident angle is equal to reflected angle, and when you join both of them, see, the reflected and the both reflected rays are diverging again, and diverging rays do not meet each other anywhere in future. So what you have to do is basically join them. Where they meet, we had started from the head, right? So another, this could be created, and this is called image. Again, it has been created due to extension, not actually meeting of the rays, so it is a virtual image again. Virtual. Is it standing or downward? It is standing, right? Because they had met from the upper side. So ahead, we have started from the head, so the image will also be the head, and any any part which is on the principal axis will always form the image on the principal axis. That's the basic rule. So the image will look upright. This is a qualitative assessment of where the image could be, but we have also formula for this. अभी वो formula क्या होता है? We have, okay, I think I did not define one thing more. Let's say this is the mirror, then it must have been taken from the sphere, right? So if you take the radius of this thing, This is r, and the half the distance is called focus. So this is a focal distance here. Focal distance. Is it negative or positive? Of course it is negative, because the sign convention says it is negative. The object, wherever the object lies, it is negative. On the other side, it will be positive. Here it is positive direction. So minus f, right? So the basic law is 1 by v plus 1 by u is equal to 1 by f. This is for mirrors, spherical mirrors. Where v is the final or image distance from where everything is measured from the pole. Image distance, this is uh, object distance, and this is the focal length. This is the mirror image, mirror formula that you have here. All right, and see, the object as we had drawn in this particular ray diagram, that the object formed smaller, right? It was a bigger object and the image formed smaller. In other cases, or depending on what distance is the or what is the distance of the image, or sorry, object from the mirror, it may appear bigger or even smaller. So magnification is equal to minus v by u. This minus represents upright or a downward. For example, if the if object is upright here, then you just have to apply c. Magnification in this case would be simply, this is v, right? It is positive and it is a negative number. So you just plug in those values as the sign convention, as per the sign convention. You do not have to forget the sign convention. And when you plug, the magnification will come up. If it is a negative number, the image is going to be downwards. If it is, let's say, minus 2, the image is going to be downward but twice the length of the object. If the object was here, then whatever length it has, the image will have twice the length but in a negative direction. That is the what minus 2 represents. If it is minus let's say 0.5, it will be again downward but half the length of the object. And the positive ones you already must be clear, it's obvious. So this was about the spherical mirror, and we have something called refraction of light. Reflection of light, based on that principle we have already discussed this spherical mirrors. Now, as per refraction of light, if light enters from one medium to another medium, it might deviate from its path. It might happen something like this. So based on what is the number is called optical density or refractive index, mu. Refractive index. The more the refractive index, the more it will bend towards the, see, from any surface, this is the surface, right? And this is medium 1, mu 1, and this is mu 2. What is this? This is normal from the surface. Then this angle is called angle of incidence, and this angle is called angle of refraction. Not reflection, refraction. Okay, if that happens, then what we have is a formula over here. This is called Snell's law. अभी Snell's law के हिसाब से होता क्या है कि sin of I upon sine of R, angle of incidence and angle of refraction, is equal to mu2 upon mu I, sorry, mu1. This is the basic law of refraction. This will determine how much the light is going to bend while moving from one medium to another medium, having different refractive indices. So this was, yes, refraction of light. Due to a very common application of refraction of light is whenever you are, let's say there is a bucket and there is a bucket and on the bottom there is an object. If the water is filled and you look it from here, let's look it from here, then the object appears to be at a lesser depth. Why? Because the this thing, refractive index of water is actually equal to 4 by 3, where refractive index of, this is water, and refractive index of air is 1. It is assumed to be 1, although it is slightly bigger than 1. The vacuum has exactly 1 refractive index. So हमें क्या दिखता है कि हम इधर से देख रहे हैं, काफ़ी बार हुआ होगा अगर हम किसी पॉन्ड में उतरने वाले हैं तो हम देखते हैं उसका बॉटम कितना है उसका डेप्थ चेक करने के लिए, बट जैसे हम उतरते हैं वी रियलाइज दैट द डेप्थ इज फर्दर हायर और मोर एज वी हैड अज्यूम्ड इट टू बी. तो होता क्या यहाँ पर, अगर लेट्स से द लाइट रे is in this direction, and then as it is coming outward to a lesser denser medium, it will not bend inwards, it will bend outwards. This is the, or this is the normal, right? Normal. Then it is not going to, this must have been a straight line, but it will not go inwards, it will not bend inwards because the medium is not higher, it is lower than 4 by 3. That is why it will reflect outwards and it will go into the eye. And if you draw from here, if it is perpendicular, if sin I is perpendicular, sin R is also going to be perpendicular. Sorry, sin I is 0, then sin R is also 0. Because if the light is going straight perpendicular to the surface, it will come out straight, no matter what the index is. In that case, what you have to do is, we draw something like this, and the object appears to be here. Because the light sees like this, right? In the direction of coming of light, and our eyes assumed it to be in a straight line, and that is why it appears to be over here, the object. Then in this case there is a formula for that. We can easily determine that actually. Let's say this is apparent depth, d apparent, and this is the actual depth, d. All right. Now this is angle of incidence, and this is angle of refraction. All right. I hope there is no problem. Now I'll just quickly derive it for you, or maybe using this color itself. Yes, this is angle I. What I can do over here is simply write sine I by sine R is equal to mu 2 upon mu 2 upon 1, right? Because the index of this is 1. Now if that is okay, then yes, sine I So can I write this as sine? If this I write as alpha and this as beta, okay, if this is alpha, this is also going to be alpha, right? As per alternate interior angle. And if this is beta, see, yes, this is a straight line, this is a straight line, this is a straight line. Okay, so sine I, can I say sine I is exactly equal to cos alpha? Why? Because both of them are 90, right? Alpha plus I is equal to 90 degree. So from here, I can quickly say that cos of alpha, sine of I is equal to cos of alpha, divided by, what is this angle? Mm, this angle. It is beta. Just a second. Yeah. So sine of beta is equal to mu 2. What is cos alpha in this case? It is going to be cos alpha, right? So from here, you will get d upon d apparent is equal to, or actually, d apparent by d is actually equal to 1 by mu. This you can remember from here. Mu is equal to real depth upon apparent depth. Although the derivation was not exactly important, you just have to remember this one. That will be okay. Now, image shift. Image shift. What is this image shift? That the apparent depth. This is basically the image shift, right? Shift. This you can also calculate, basically d minus d apparent, nothing else. So if you just have to remember this one, and this is the basic Snell's law. This is very important. Now coming to critical angle. Okay, let's take this case. If light is coming in this direction and this is a denser medium, is higher than 1, and this is air having density of 1 or refractive index 1, then light is going to bend outwards, right? Okay, now if I increase the angle further, the light will bend further. Do you realize that there is going to be an angle such that the angle of refraction becomes 90 degree, and it actually goes in this direction, so it never leaves the surface of water, basically, right? In this case, let's draw the perpendicular, and this is the angle of incidence and this is the angle of refraction, r, and this is going to be 90 degree. Then what is this angle at which the light actually never leaves the surface? That I will call critical angle, because when you have light not leaving the surface, then the upper person, a person from here, would not be able to see what is inside the surface, or the all the light that is there would remain inside the surface itself. That is called critical angle. That will be I. Then just apply the Snell's law. Sine I upon sine r. What is the refractive index of here? 1, and this is mu. So 1 over mu. Now sine of I is, let's remain as such, And what is r here? R is 90 degree. Sine of 90 degree becomes 1 is equal to 1 by mu. So I, which is the critical angle, is equal to sine inverse 1 by mu. This is called critical angle, and after which, let's say you increase the angle of incidence further, then no light is going to refract and all of the light is going to just reflect. Just reflect. Any light which is having higher incidence will just reflect inside the surface and no light will come outside. So this is called total internal reflection. Total internal reflection. And the angle, the minimum angle for total internal reflection is the critical angle, which can be found out from this particular formula, which is very easy to remember even. So this is the critical angle. All light which is having higher angle of incidence than the critical angle will just reflect inside. Now, surfaces, spherical surfaces, refraction. So basically it is talking about, let's say you have two surfaces, or this is a spherical or sphere, sorry, spherical ball, not a spherical shell, it is a spherical ball. Now what I do is cut a section over it such that it is part of another circle which is having the radius same radius. Then this section which has been cut out, I can take it out. This is called a convex lens, because you must be having some experience with the lens itself. So this is a convex lens, and whenever, let's say you have this section outside here, right? So this sphere looks something like this. All right, what you do is cut a further section in this one of the same this thing radius, and this section that you have here, this particular section you take out, and this is called a concave lens. Concave lens. Now what you can do is draw principal axis. This is the focal point. Focal point is basically when this was a particular sphere, then what was the radius of that sphere? Half of that is focal point. This is the pole, and this is the principal axis. Principal axis. And what you can do over here now, you can place the objects here, here, wherever, and based on that you will have particular images in the same manner that we had discussed in the रिफ्लेक्शन फ्रॉम द स्फेरिकल सर्फेसेस, ये हमने किया था ना, वहां पर जो भी हुआ था यहाँ पर भी सिमिलर पैटर्न क्रिएट हो सकता है, मतलब कि वर्चुअल इमेज, रियल इमेज एंड magnification, things like that can happen over here as well. Now in this thing, in lenses we have formula 1 by v minus 1 by u is equal to 1 by f. It's just a minus and plus of a difference with respect to the formula for the spherical mirrors. This is applicable for both concave and convex lens in the same manner that the mirror formula was applicable for both concave and convex lens mirrors. And magnification in this case, you already know the term magnification, is going to be v by u, not minus v by u. All right, lateral magnification, if I can say so. So this is all right. Just a second. I think they are talking about two different mediums. No problem. Let's say you have this system in which this is the principal axis and this is medium mu1 and having a refractive index of mu2. All right, then you can apply this formula, particular formula, that mu2 by v minus mu1 by v is equal to this thing, and lateral magnification could be found out in the same manner. As I told you, this is a more of a formula based chapter actually, but I don't think you need to remember more than this. This is more or less sufficient in all the cases. Now you have something called Lensmaker's formula. Basically what you do is, in this case, yes, basically for making a lens, one has to take a sphere and cut one section. Now this particular arc could have one radius r1, and this particular arc doesn't have to be the same radius, right? It could even be a bigger arc, a thinner arc, and based on that it could have several radius, even longer r2, even a shorter r2. So r1 and r2 could be different. This is exactly how one makes lenses. A side could be thinner. See, a lens could be like this, right? A lens could be even like this, where these two surfaces have a different radius of curvature. Then in that case, the lens maker formula, as per the lens maker formula, you can derive the this thing, v and u. What you have to remember over here is this one, or just the formula that 1 by v minus 1 by u is equal to 1 by f dash, or total focal length of the lens. Whatever lens, it can also have a focal length, or the total focal length. And the total focal length could be found out like this, in this manner: mu2 minus mu1, sorry, 1 by f is equal to mu2 minus mu1 by mu2, sorry, mu1, multiplied by 1 by r1 minus 1 by r2, right? You just have to remember this one and not this one, just the basic formula: 1 by v minus 1 by u is equal to 1 by f. These two would be sufficient for the lens maker formula, because remembering a long formula can be hectic sometimes. So you can divide them into two parts, and rest of it is very straightforward. The same, the lateral magnification have the same formula, v by u. Okay, so this was about yeah, we have not talked about prism till yet, so we'll talk about it. See, prism is pretty basic. This is a isosceles prism in which there is a particular prism angle A, and these two has to be the same. If you know A, these could be easily found out, because this is a isosceles triangle. And let's say light enters from here, goes here, and then comes out. Then this was the original path of the light, right? While this is the new path. This is the total amount that of angle that the light has actually deviated due to the prism, right? So angle of deviation could be found out in this manner. Just a second. Where this is angle I, this is angle I dash. So I minus I dash minus A, simply that. And minimum deviation, you have this formula, and maximum deviation. These I don't think you need to remember, but still, if you can, it's easy. Now, scattering of light, you already know that when light particles, due to the interaction of light particles with the particles in the sky, they actually deviate from the path. That is called scattering of light, due to which our sky appears blue. That is a not so important part of this chapter, pretty basic. Now, coming to this part, this is not at all important. This has been removed from your syllabus, optical instruments. And it's just that power I will define here. Power is simply 1 by f. Power means what is the power to bend the light. If it is like this, how much it can deviate, how much it can make the rays of light deviate from their path. That is called power. And you already know that the thicker the prism, the more the power. Basically, if you have a thicker prism, the focal length is going to be shorter, right? Because it is having a less radius of curvature. So less radius of curvature means lesser focal length, and lesser focus length basically means more power. So power is defined in such a way that power is equal to 1 by f, 1 by focal length simply. And whenever you have two optical instruments, let's say a lens joined by another let's say concave lens, then the two of them can behave in, let's say the light will come here and come here, and then due to the second lens it will diverge, right? So the net effect of these two lenses could be combined in the focal length or the powers. Power is going to add up. P is equal to P1 plus P2, where P1 is equal to simply 1 by F1 plus 1 by F2. Okay, so that is one part, and this you do not have to worry about optical instruments. So this was the ray optics that we have discussed over here, and we'll talk about the wave optics now. This is again very just straightforward, uh, formula based, nothing else. So this says that light can also behave in a, so this is the particle theory, that light has particular particles, these are called photons, and they behave such in the same way that a ball does, that it will go in the straight line when given a velocity and things like that. But the people, like this was propagated by scientists like Newton, and there were other scientists who were of the opinion that light is not a particle, it is actually a wave. It goes like this. One of the leading scientists was Huygens, who propagated the wave theory. Actually, it turns out that neither of them were wrong, and light has a dual nature. We'll talk about in the next chapter that actually every particle in the universe has dual nature. Everything is a particle as well as a wave. Now, coming back to this specific part, yes, wave optics, and we will start with waves. Waves, you must already be knowing that a wave has certain amplitude and intensity. Intensity is proportional to a square, things like that. Other things are also there inside the intensity, but we'll mostly focus on the amplitude. What is the dependence on the amplitude? And amplitude, wavelength, everything you must be knowing by now. So I need not discuss all that. This is something called wavefront. Basically, let's say you have uh, a ball that is dropped in a pond. Then when you look it from the top, then it appears to be in concentric circles, right? All the surfaces which are slightly above the surface of the water, they appear to be in a concentric circle. Then all these points which are in phase, having no phase difference between them, these are called the locus of these points. Whatever shape they form is called a wavefront. All right, this is what they are talking about. Locus means basically the shape they form together. The particles in a circle, they together form the circle itself, right? So the circle itself is a this locus, locus of all these points. Now we have something called intensity. So intensity, basically intensity is power divided by area. Power that is radiated by this source in the form of waves, and this is one wave. When it travels, it could take a shape like this, it could take further shape like this. This is an example of this thing, a wave in a pond. All right, then the intensity at this point could be calculated by the power consumed. I is equal to power consumed by the area over which it has been distributed. So 4 pi r square, right? Or if you only talk about the length, then pi r square. In the 3D, it will be 4 pi r square as per because point source that will radiate energy in all the three dimensions. But this is a two-dimensional wave, so pi r square. Anyway, it is proportional to 1 by r square, right? And I already told you that intensity is in proportional to a square. So from these two, can I say that A is actually inversely proportional to 1 by r? As the distance increases, the amplitude of the wave will decrease in this fashion. And the intensity will decrease further by 1 by r square. So this is what this is talking about for spherical wavefront. Um, let's talk about something called, let's talk about something interference first. Otherwise, it will be difficult for you to understand the Young's double slit experiment. So let's take a wave, two waves actually. One is like this, and another wave is a same copy. Then if you add them up, means these two waves meet each other, then basically all the points which are above here, they caught up in phase, right? They are in phase. Now the resultant of them will look something like this. All right, so basically the amplitude gets added up, this a1 and this a2. So a1 plus a2, right? In this interference, this is a constructive interference. There could be one case in which the other wave looks like this. And this point is in the negative axis, and this point is in the positive axis. When you combine these two, the wave will actually look something like this. Nothing. It is nothing here. So this is called destructive interference. The waves are interfering with each other, right? Destructive interference and constructive interference. Interference. So in constructive interference, a1 plus a2, and even in this case a1 plus a2 happens, but the a2 here, a1 here is negative. That is why they get cancelled out. Or if you have unequal, then the resultant will look something like this. If this is bigger, a1 is bigger than a2 here, then the resultant will look something slightly in the positive direction. Okay, if they're exactly equal, they will cancel each other out completely. So complete constructive interference and complete destructive interference we already talked about. For constructive interference, the phase difference has to be 0, and for destructive interference phase difference has to be pi. If that is clear, then yes, coming to the intensity. If the A1 and A2 are getting added up, it is not the intensity which is added up. It is the individual amplitude which is getting added up. Now, what was this? Square dependent on A square, right? So I can say A, right? When A gets added up to another one, then it is the under root form of I which should get added up, right? So for constructive interference, this looks like this: A net, I net. And for destructive interference, it should be like this: I1 minus I2 is equal to root I net. So when you square them, it becomes I net, and when you square them, it becomes I net for constructive and destructive. But for a general case, I will give you formula for a general case in which phi could be anything. The difference in the different phases, or the phase difference, is could be any angle. Then I is equal to root I1 plus root I2 plus 2 root I1 I2 into cos phi. The whole thing squared. This is going to be the intensity for the in any type of interference. This is what I talked about. I already covered this one. Um, let's come to the most famous part of this chapter, that is called Young's double slit experiment. What he did was, this is let's say a source of light is here. A source of light is here. Then it will emit light in all the directions, including these two directions. All the light that is getting reflected over here, it doesn't matter. Only the lights which are passing through these two slits, they will appear on the screen. Just a second, just a second. Yes, this is a screen. And as per this particle theory, there should be a light here, a light point, and a light point here. There should be no other points which could be bright. Only these points should be bright as per our this theory, particle theory. But what happens is, for example, just forget for now that this is a particle or this is a light. Just imagine that to be a wave. All right. Then these 2 points would also start to emerge waves. These two particles also start to emit waves. Now, do you understand that whenever these two waves are meeting, they must be interfering positively, constructive interference? So, as per wave theory, whenever, let's make it bigger and bigger, and it happens that these points, uh, just a second, yeah, if these points are kept on the screen, they will appear to be bright. So, there could be several bright points, right? Isn't it? As per the wave theory. there could be several bright points, and these are called fringes. If particle were to behave as a this light has to behave as a wave, then it should not only produce these 2 points. No, it should actually produce multiple fringes. And this is what exactly is observed, that whenever light is passed through these two slits, it produces fringes on the screen, multiple bands of light, and these are shadows or nothing, dark. So this is bright fringe and this is dark fringe. This is the basic explanation of Young's double slit experiment, and I'll talk about what is the quantification. Yeah. So the width of any fringe, or the distance between two consecutive bright fringe or dark fringe, is found out by d lambda over small d, where d represents this distance and small d represents the distance between the two slits. All right. So the distance between two bright fringes is simply d lambda upon small d, the distance between them, and the distance between these one dark fringe and the next dark fringe is the same, is also d lambda upon d. So if you calculate the nth bright fringe from here, the distance between the central, this is central fringe, central, because it appears to be in the middle. And whenever you want to find the distance between the central fringe to the nth fringe, it is going to be simply n d lambda over d. Okay, d is the distance from the slit to the screen, and small d is the distance between the two slits. All right, so this is the basic of uh, double slit experiment, n lambda d by d. This you do not need to remember, further complication they have done, but it's just that you can imagine this one. If you have this diagram in mind, they might ask you that what is the distance between third bright fringe and fifth bright fringe. You can just, based on this, you can, that the basic rule is that distance between one bright fringe and the second bright fringe, or two consecutive bright fringe, is this one. Based on this data, or one dark fringe and the second dark fringe, next dark fringe is the same. Based on this, you can find out whatever they want, from this dark fringe to the second bright fringe, anything. Okay, so this was Young's double slit experiment. Only these two you need to remember, no problem. Or even only this one you remember, it is going to be fine. This is part of the explanation actually, how it came up to be this. For a bright fringe, n lambda, and for the dark fringe, it is n plus 1 by 2 lambda. The phase difference, because it has to interfere, right? If the both the light interfere with the same angle, or if the phase difference between them is 0, then it must mean that it is going to be in the terms of 2 pi or 4 pi, 6 pi. In that case, the difference between the path length is going to be lambda, 2 lambda, things like that, right? When the path length or the phase difference is going to be pi, 3 pi, things like that, then the path length difference between both of them is going to be lambda by 2, 3 lambda by 2, things like that. So this is a explanation for this, but you need to remember only this part. This is for the understanding. Coherent source, I already told you that whenever two sources are in having phase difference of zero angle, 0 degree, then these are called coherent sources. Now diffraction. Basically, let me discuss it over here. Here, I'll just erase this part. Yeah. So basically, this diffraction is basically, let's say you have a slit, a single slit, and the light starts from here. Then, and this is a screen. Then, as per your observation, it should be like this. The bright fringe should appear like this. But actually, the moment it starts from here, it start to travel as a wave. And as the wave touches the screen, it produces certain bright band and the lesser intensity band. So central maxima, so the central will be a maxima and then a minima. The intensity will decrease and increase. It is very similar to the Young's double slit experiment, but it is slightly different. Then there you had fringes, particular fringes, but here you have a wave-like structure. That intensity might look something like this. This is the intensity graph that I'm drawing. That at this point, highest intensity, at this point, lesser intensity, and this is like this. So, uh, angular width. Actually, they have given opposite formula. It is not this, it is rather 2 lambda by b. When you want to find out the distance between the width of the central fringe, then it is going to be 2d lambda upon b. Alright, where b is the width of the fringe, width of the gap or the slit. D is the distance between the slit, the this particular apparatus in which the slit is there, and the screen. And lambda is the wavelength of the light that is being used. So this is for the angular width means basically if you have like this, then what is this angle? Alpha. And what is this? X. This is given by the formula, this one, and this is given by the formula, this. All right. This is for the central bright fringe. Central bright fringe. For the nth bright fringe, you have this formula for the central bright fringe. So this was diffraction, very similar to Young's double slit experiment, but basically there is a difference here. Now you have something called polarization in this chapter. So this you do not need to remember. Optical instruments, resolving power, no need. It's just that polarization I will discuss over here. So basically polarizer is a material in which a light is generally mixed, right? It has certain let's talk about only the electric field part. Then it is moving in this direction, some is moving in this direction, and it is mixed of all the directions. When you pass this light through a polarizer, it doesn't allow all of the light to pass through it. It only allows a certain let's say only this part. It doesn't allow the intensity of electric field that is in this manner. No. So the light gets polarized. This is polarization, and this is a polarizer. Then if you have a polarizer, then basically what you're getting rid of this whatever electric field as perpendicular to the this particular angle, right? Then we have something called Brewster angle. Let's say this is water or any medium, other medium, and light actually comes in this direction and refracts, and it also reflects. Then the angle at which it is perpendicular, the reflected ray is perpendicular to the refracted ray. What will happen in that case is that the light will have lost all the components which are perpendicular to the component. Let's say it is in y direction, y, then all the components which are in, let's say this is x direction, then all the components which are in z direction of the intensity of the light, it will get lost in the form of refracted light. Then this light will be called polarized light, and this is called the angle at which, the angle of incidence I, at which this happens, that the refracted and reflected ray are perpendicular to each other, that is called Brewster's angle. Brewster's angle is that angle of incidence that gives you polarized light. So it is this. All right. So this was Brewster's angle, angle of polarization. You can also call it polarization angle or Brewster's angle. And this is what we have already discussed. So I think that was all for the topic of optics.